Hello, in this video we're going to be going over the Sooper Dooper Looper lab from the Additive Manufacturing class. So getting started, before we get into 3D printing or CAD, we first need to do some math to figure out just what general heights to make various features with a given loop size. Okay, so we'll get right into it. So what we have is a ball, okay, that'll be set on top of some unknown height hill, okay, and it has to travel down a ramp and around a loop of given radius, or of given diameter, I should say, and then it'll go down into this slow downhill here, which is sort of like a quarter pipe, and eventually rest here somewhere in the middle. Okay, so there are two more or less critical positions that we need to sort of solve for as we are sort of figuring this system out. Okay, so what we have here is state 1 and state 2. So state 1 up here and state 2 over here. Okay, now the problem statement wants us to figure out at what height up here when the ball is dropped does it go down and go fast enough to where it stays in contact with this loop, which is just a simple radial path at all times. Okay, so at state 2, we've highlighted that one because at this very instance, the force of gravity is going to be what's bringing us directly downward. Okay, so that's going to be Fmg. Okay, and then what's pulling us up, or in this case, away from the center of the circle, okay, of radius r, so we're going to call this r loop, okay, is going to be, your radial force, so F radial, which is going to be equal to, okay, m, mass of the object, times v squared over r loop. Okay, and since this is at state 2, we're going to call this v sub 2. Okay, so let's sort of so we could use these equations, okay, to sort of figure out what the velocity at the height of the high point of the loop here needs to be. Okay, so let's go ahead and do that. So we know f your Fmg is going to be equal to F radial. Okay, and what that is basically saying is the mass of the ball times g, acceleration due to gravity, which is 9.81, okay, is equal to that same mass times v sub 2 squared over r loop. Okay, and I'm going to be critical about r loop because there will be another radius of the ball. I'll just draw that out right now. R ball as well. Okay, so anyway, let's continue with solving for this v2. All right, so m's are going to cancel out. These are going to be the same mass. Okay, next what we can do is we could say that g is equal to v2 squared over r loop. Okay, so spell loop correctly. So the gravitational acceleration is equal to radial acceleration at this point. Okay, that makes sense. We could further decompose this and say v2 squared equals g times r loop. Okay, we could further say that v2 is equal to square root of g times r loop. Okay, pretty simple. Okay, so now how do we get this velocity to be that fast? I guess, sort of poorly worded there, but how do we get the ball going that fast at that point? Okay, well, we have to bring it up to a certain height here. Okay, so we're going to call this height h sub 1, okay? And for good measure, we'll just call this one over here h sub 2. And again, these both start out at the same 0 point, whatever it might be. Okay, so potential energy in general is going to be PE, which is going to be equal to mass of the object times g, acceleration due to gravity, times h, whatever that might be. Okay, potential energy at state 1 is then mass of the ball times g times h sub 1. Okay, potential energy 2, there is going to be potential energy at state 2. Anytime it's, above our 0 point here, we could say that it has the potential energy of the object has, some effect on the system. So we're going to say PE2 is equal to m times g times h sub 2. Okay, now we'll also have kinetic energy. Okay, so the ball, as it's traveling, okay, will be in contact with the surface. Okay, so it'll have a forward velocity v, okay, and it'll also rotate with a velocity, rotational velocity omega, okay, and that's in radians per second, okay, and your velocity should be in meters per second. Okay, I'll give you a loop diameter in millimeters, but obviously you'll be able to convert that pretty easily into meters. Okay, so anyways, your kinetic energy here, so that's the energy as it's moving, will come in two forms. So you have kinetic energy in general, which is going to be 1/2 mv squared plus 1/2 I omega squared. Okay, and again, this decomposes into your sort of forward, I don't want to say linear because we're going to be going through all these sort of elements, including a loop. And then this is going to be the rotational. Okay, and again, it's rotating about its own center. Okay, so it rotates in the loop, but when we say omega, we mean it's like rotation as it's sort of rolling along a surface. Okay, so we'll try and not get those two confused. And we could also say kinetic, sorry, I wrote a P. Kinetic energy at state 1 is equal to 0. Okay, obviously because we're going to say it's just barely started and the velocity is going to be 0 at that particular point. Okay, kinetic energy at state 2, however, is going to again be 1/2 mv sub 2 squared plus 1/2 I omega 2 squared. Okay, so now we're left with some questions from those two equations, or from, I guess this equation here. Okay, so what is I and how do you find omega? Okay, so let's tackle the omega issue first. So if we know the rotational speed, the forward speed of the ball, and we know that it's staying in contact with the surface at one point at all times, then we could say that like it travels one rotation every time it's gone linearly the distance of one rotation. Okay, so the distance of one rotation is going to be very simply the perimeter. Okay, and the perimeter of the circle here is going to be 2 pi r sub ball. Okay, so this is r, the radius of the ball there. Okay, so we could say omega 2 is the rotational speed in radians per second of, one rotation. So that'll be v sub 2 over 2 times pi times r sub ball. Okay? Now, confusingly, so this is your, as it stands right here, this is your rotational speed in revolutions per second. Okay, and as I said before, you want radians per second for your omega. So you basically just have to multiply this by 2 pi, okay, because there are 2 pi radians per every rotation. Okay, so kind of confusingly, the 2 pi's will cancel out in the numerator and denominator, leaving you with V2 over R, okay, which actually tripped me up when I first learned about this. Okay, so anyways, and this is our ball, okay, the radius of the ball. Okay, so anyways, that's how we find our omega 2, okay? And again, our omega 1 will be 0 because when V goes to 0, omega also goes to 0, okay? Now, next we'll go about finding our I, our moment of inertia. And I guess for that matter, our mass as well, okay? Because as of right now, that is unknown, okay? So if we want to find the mass, we know the radius of the ball is going to be 1/4 inch. Obviously, we're going to convert everything into kilograms, meters, and seconds when we do all these calculations so that it all works out neatly. I've given you the radius of the loop in millimeters, and obviously I'm giving you the diameter of the ball in inches because that's how I purchased them. Okay, so anyway, what we could do to find the moment of inertia, we'll first find the volume. Okay, I'm going to use capital V of this in this case. I'm going to say ball to denote volume of the ball. Okay, you know the volume of a sphere is 4/3 times pi times r of the ball to the third. Okay, you could then find the mass. So we could then find the mass. And I'm going to use m because everywhere else is m, which is going to be just m, which is equal to v, sorry, accidentally wrote velocity, capital V, ball, times rho, which is the density of steel. Okay, so we'll look up the density of steel and we'll apply that to the ball. Okay, we could also weigh the ball to backtrack this, but it's kind of fun to do the math. Okay, so anyways, after we find the mass, we could then find the moment of inertia, which is going to be equal to 2/5 m r of the ball squared. Okay, so great. We have now all of our unknowns apart from one, which is going to be our H1. Okay, so we know H2. That comes from we could derive that from the radius of the loop. Okay, so we could say that our H's both start at the very bottom of the loop, okay? And we could say that H2 is very simply equal to the diameter of the loop, okay? Equals DIA loop, okay? We don't know H1. We know the mass because we know the diameter of the ball and the radius of the ball, and we know a bunch of other things as a result of that. Knowing what velocity we need at the top of the loop, we could find the kinetic energies because we're able to find the omega. Okay, so yeah, now what we could do is say that the energy at state 1 is equal to the energy at state 2. So we could say very generally PE1 plus KE1 is equal to PE2 plus KE2, okay? In this system, we have neglected work done by friction, okay? That will be at state, that will be at play, I should say, when we do this in real life, and certainly after we test this when we print this. Okay, I will give you a fudge factor, but we're not going to account for that in these equations. We will, however, do a motion study in SOLIDWORKS that will be able to account for this sort of thing. Okay, so anyways, generally we have no kinetic energy in state 1, so that'll go to 0. But if we write this out in long form, we end up getting m times g times h1, which is our unknown, is equal to m times g times h2. Okay, that's the potential energy at state 2, plus 1/2 m v sub 2 squared plus 1/2 I omega 2 squared. Okay, and then we can very simply divide each side by mg, the product of mg, okay? and we get H all by itself. Okay, and we could solve for H1. Now, I will tell you just, as a fudge factor for the little bit of friction, we're going to increase H1 a little bit, even though we're going to keep the diameter of the loop the same as what you guys, were given, just so that we know for a fact that it'll go around the loop. This would be giving you the minimal height you would need to make this, even if friction were to be neglected. We're going to give it another 30%. We're going to call this H sub star equal to H sub 1 times 1.3. Okay, and that should give us enough added height to have enough energy to comfortably get all the way around the loop. Okay, so thank you very much for watching. In the next step, we will go over what we need to do for the CAD and simulation. In this portion of the video, we're going to actually go about modeling the loop and ball and doing the motion simulation. So let's get started. First thing we're going to do is we're going to model the ball itself. So it's 1/2 inch diameter ball. So what I'm going to do, let's go and grab the center point line or the midpoint line. And we're going to go at the origin, and then we're just going to make a vertical line. Okay, so it starts at the origin. And then what we're going to do is we're going to create a 3-point arc that connects these 2 points. Okay, so making the arc, and we are very simply going to make it a 180-degree arc, such that, as we revolve this, we can make a sphere. So that's all we need to do. And let's just make sure that the midpoint of the arc is coincident there at the origin where we started our midpoint line. Okay, I'm going to dimension this to be, dimension this to be 0.5 inches. Okay. Yeah, the ball is, I gave you a half an inch sphere to make this out of, or to roll down the track. So that's what we're making it. So that's all we really need to do to this sketch. I'm going to exit the sketch, and now I'm going to do a revolve boss base, and I'm going to select at the axis of rotation that middle point. Okay, and if you don't have what I see, you could just go to selected contours and select whichever contour is of interest to you. Okay, but if you keep the sketch highlighted after you make it, like if you just go to exit sketch and then immediately go to revolve boss base without clicking anything else, it should stay selected. Okay, and you select obviously the straight line as what you're going to revolve it around, and we've created our sphere. Okay, the next thing I'm going to do is actually specify a material type. So we're going to go to edit the material, and we're just going to call it, what is this type of steel? Okay, I think we should go, let's just go with the 1045. I think that should probably be close enough. Let's take a look. What's the difference between 1045 on the density? Where's the density, mass density, 0.28 versus alloy steel, which is 0.278. What was that? 304, 0.289. Yeah, so it varies by a bit, by like a 30th or whatever. Okay, so I'm okay with that. We're gonna keep with this ASI 304 steel ball. Okay. And we're going to apply that mass to it. All right, and we'll close out of this. And there we go. We've created our ball. And next we will tackle our loop. So now we will make our loop. Okay, so the loop I'm going to make for you today is based off of one that I made a while back. I've given you guys metric units, which is how you're going to make yours. I did my calculations in metric and then rounded up to the nearest, half an inch or whatever I did, for my loop. But you guys will try and keep everything in millimeters. I'll do it this way just so that you guys aren't able to use my exact numbers here because I'll have you guys do it in metric. So yeah, let's just get started. This is going to be in inches. I'm going to want you guys to do it in metric, but I want it to be slightly different from what you guys are doing. Okay, so first thing we're going to do is sketch on the front plane. What I want to do now is create a skeleton sketch. Um, of what the hill and loop will look like for our loop. Okay, so we're gonna make the platform that the ball will sit on as it starts. We're gonna make a line going down, and I'm gonna make an arc now, and we're just gonna make it, go to flat like that, so horizontal. Okay, and then we're gonna make another upward arc. Something like that. Okay. And then we're going to finally make one more vertical line. Okay. Or tangent line, and we'll make it vertical. So now we're going to make some relations. Okay. So we're going to make sure that this one and that one are tangent, which they are. We're going to shift click the arc and that horizontal line. We're also going to make sure that that is tangent. Okay. It wasn't. We're also gonna, yep, that's tangent as well. And so is that. Okay, that's looking pretty good. Now, again, I'm gonna refer to the previous numbers that I used for my desk toy. So let's do smart dimension. We're gonna go from the hill down to here, and we're gonna make that 3.5. Okay. And then we're also going to go from the top point down to here, and we could just make that equal to that one. Okay. And we'll hit check on that. Now what I want to do is actually add the loop that we want. Okay. So let's create a circle, and we will make the center point right at the center point of the previously made arc. And we will also make this one for construction. Okay. So now we've positioned our loop radius. Okay. Now we could smart dimension. Again, I'm going to make mine 2 inches. Yours will be not standard units. It'll be metric. Okay, cool. A couple other things I did. I made my angle here 120 degrees. You should note that our hand calcs don't anticipate any any friction. Okay, so we're just going to do, very basically without friction. We do account for the rotational speed of the ball, as you know from previously in this video. But yeah, we're going to keep that angle to 120. It would probably go faster initially if you made that angle steeper, like if you made that ramp steeper. But as it hits this radius here, you could have bouncing, or it could like decide to leave the surface a little bit. So I found like 120 is good. You could totally stick with that one. For me, I'm gonna make my platform just about the size of the ball, so zero point 0.5, or I guess the diameter of the ball, and that seemed to be a good enough platform when I made this the first time, so I'll stick with it now. And then what we'll also do is let's just make the distance from there to there. Let's just make that, let's see what happens when we make 1.5. Okay, that doesn't look too bad. Again, we're trying to keep in mind we want this to all fit on the prusa that we have. I'm also going to make this arc and this arc of equal curvature. Okay, what are we missing now? Oh, that's not vertical. That would help. We're going to make that vertical. Okay. And again, we're just making this as like a backstop so that the ball doesn't, go flying. I made a little bit of a fancier one if you saw it previously in class. It has like a ball catch on the other side. You could totally be creative with this exercise and, have however many elements as you want, as long as you have the hill and a loop and do calculations that show me that you anticipated the size and everything like that, then that's what I care about. Okay. So yeah, that should be good for this sketch. We're gonna click check on that one. Okay, and we'll exit the sketch. So now what we're going to try and do is eventually we're going to try and make a 3D sketch that, does the full corkscrew and the slow downhill or whatever you want to call it. But first we need to actually make the helix. Okay, so we're going to go to curves and we're going to go to helical and spiral. Okay, and I'm going to select that guy there. Oh, no, yeah, it asks you to do that. So you gotta select the plane. It's a good thing that we made that circle, but we now have to select the plane that we started from, and then you gotta make a circle, annoyingly. So it makes you make the circle, and it's kind of always helpful if you already have a circle made, because then you could just go to its endpoints, and you have your circle. Okay, so I'm gonna click check, and then exit sketch. And if you only make a circle, it'll end up doing your helix for you. So now that we're in here, I've pre-selected all of this stuff. Okay, well, it selected it for me, I should say. I did this just before I made this video, so all these are, basically what they were when I first made this, so I know these work. But basically, you want to start it at 210-degree angle. That is the correct starting point from, our 120-degree angle here. Okay. Yeah, and basically, I think that 210 degrees is from vertical all the way around this way. So if you're vertical like that, as I'm facing, the screen, I go around 210 degrees, and that's the start point. Okay. You then have to specify how many rotations, and we want it to go enough rotations to where it stops at the bottom. Okay, so what that ends up being is 1 1/6. So you could say that's 7/6 of a rotation. Okay. And if you hit enter on 7/6, that ends up bringing you back around to the vertical point. Okay. Now, I plan to make my particular loop, or my, let's say the cross section of the loop I want to support my 1/2 inch ball. Okay. And so I'm going to try my best to make the track uh, only 5/8 of an inch wide, or 0.625. Okay. So yeah, what that'll mean is, like, if I have this 0.75-inch pitch, that means like the track won't clash with itself. Okay, which will be important for the loft to generate. Okay, so you can make your pitch a little bit bigger if you do want to make your track a little bit wider to accommodate the ball. I've found that this is sufficient. You could do the same as mine. Again, everyone will have different loop heights. And yeah, really, I guess the tracks can be similar, but you could certainly go off script from what I'm doing right now. Okay, so that's why I've selected 0.75. I could make this more or less, depending on, if I had a different ball, or if I just wanted to make the track a little bit wider. Okay, should know a couple of things are at play here. If you have a very, very wide track for the ball that goes in it, it might move around to the sides. Generally, there'll be kind of less friction, because on a very flat surface, a ball has a very small contact patch. But as a ball is rolling, like, and it's meeting like a curvature, like, there's a lot more friction at play there. Okay, so if you wanted to make your channel a little bit wider to accommodate that, and maybe perhaps reduce friction, that could be a strategy. However, if you also, it works the other way as well, because if you make your pitch a little bit greater, then your ball has to turn a lot more, which also induces a lot more friction. So if the ball is just going in a straight line and it doesn't have to, like, turn, like, and therefore be forced up against the sidewall, you could have some losses there as well. So there's a bit of a balance. I found a track width of 5/8 of an inch and a pitch of 0.75 seems to work pretty well with the marbles that we have. Okay, so enough about that. Gonna hit check mark on that. Okay. And now what we're going to do is make a plane. Okay. So what I'm going to do first is I'm going to click the endpoint of our spiral there. and I'm going to go to reference geometry, then plane. Okay, now the plane is not fully defined yet, and we're going to go and fully define it by selecting the front plane as well. Okay, so I've made two parallel planes and the plane, or sorry, I've made one parallel plane from the front plane that is coincident to the end point of our helix. Okay, clicking check on that, and we've made our plane. We'll use that in a minute when we make our 3D sketch. Okay, so now we're going to go to sketch, do the drop down from sketch, do 3D sketch. Okay, and I'm going to grab the line tool. Okay, now this is going to, yeah, there we go. We're going to go there to there and then down to there. Okay, now we're gonna hit escape for now. Um, because to make the helix, we're actually just going to select the helix itself. Okay. And then we're gonna just do convert entities. Okay, and that very simply makes the helix into a sketch entity. Okay, and I'm gonna make sure that these two are attached. So you see that they're attached. That's not the right place for it. I'm gonna have that go down there like that. And I'm also gonna make that guy and that guy coincidence so that my 3D sketch is fully defined. Okay, cool. So I know those two are attached and that's good. Now what I'm going to do is I'm going to grab my line tool once more and I'm going to start to mock up the other portion of the track. Okay? So doing like we did before, making my arcs and then having another one that's going up straight from that. Okay, so now what I'm going to do is I'm going to, just be lazy and make sure both of those match by shift clicking my first sketch to the corresponding point on the 3D sketch, and I'm going to do a long Z. Okay, so if you see the plane that I started in, the Z axis is the one that is like, sort of going through both of these parallel planes that I've just made. Okay, so I'm going to do a long Z for that. Okay, then I click check on that and I'm going to rinse and repeat for all these other guys. So shift clicking both of those, going to do a long Z, and then we're going to do shift click on that one and that one. Whoops, I have the plane in there. I'm going to delete that selection and I will make them a long Z together. And that one's a long Z. That one's a long Z. Why is this still? Oh, I know why. So now what we're going to do is we're going to actually shift click the line and the arc, and we're going to make them on the plane. Okay, so yeah, it did it automatically for the arc. So now we are fully defined. Okay, we're going to exit the sketch here. Okay, now we're going to go about making the track. Okay, so what we're going to do is we are going to go onto our front plane. So if you were following along and you started the sketch at at the origin and then you went off to the right, or I guess the left, it doesn't really matter, but either way, if you start at the origin, then that first point will be at the right plane, which is going to be convenient because we'll go ahead and sketch on that plane. I'm going to flip it around actually. So now what I'm going to do is I'm going to grab the center point arc. Okay, so if you don't have it looking like this exactly, you could do the drop down and you could find the center point arc. What I'm going to do next is I'm going to go to the origin. I'm not going to click on the origin. I'm going to go directly above the origin. As you can see, it gives me that blue dotted line indicating that like I'm directly vertical from it. Then what I'm going to do is I'm going to go down to the origin, okay, and then out to the right hand side, or you could go to the left, okay? And we've created the arc that'll make up like sort of the contact surface for the ball, okay? So next what I'm going to do before I start dimensioning things, I'm going to make sort of like the outer portions. Going to make a small line coming out from there, and then another line going directly vertical. And then I'm going to go directly horizontal once more and go directly underneath the uh, the origin. And then another one directly vertical back to the origin to create a closed shape. Okay. And the dimensions I used, so I'm going to measure the width here. Okay. I want it to be 0.625 after I mirror it. So I'm going to do 625 divided by 2, again, because I'm going to mirror it. Okay, cool. And let's see. Let's see. I think I actually remember. I don't need to do that. So I'll do this one. I made 0.1. Okay, this one I can make 0.25. And the last thing I need to do is dimension the arc radius, which is going to be sorry, zero point 0.3. Okay. I made it a little bit bigger than the radius of the ball, which is 0.25, half-inch diameter ball. Oh, and there's one more thing we need to do. What is that? What is the last thing we need to do? Oh, that's what. We need to make sure that that origin that is directly above the origin. So I'm going to grab a center line, go from the midpoint of the arc, or the center point of the arc, I should say, and go to the origin. And then I'm going to make that line vertical, and that'll fully define us. Okay, cool. So we're fully defined. Oh, but one last thing, I'm going to actually make this line for construction. And then I'm going to mirror that shape. Okay, so we're going to do mirror entities. I'm going to select this guy, this guy, this guy, and this guy, not the middle one. And then we're going to mirror, going to go over here to the left-hand side in the other box, and we're going to mirror about that middle one. Okay, cool. So we've created our little track surface, and that should be good. Okay, cool. Why are you now not fully defined? Let's see. Here we go. That did something. And what's happening here? Oh, okay. I guess I need to redimension to 0.1, even though I don't think I deleted it. Anyways, make this 0.1 once more. Okay. Oh, and we're still not fully defined? Uh, oh, you're not at the center point, or you're not. That's silly. And we'll shift click that one to that one, and we will make it coincidence. That'll do it. Okay. Funny, after you mirrored it, it undefined itself, so you just had to add some new relations. Okay, great. Exiting that sketch. Okay, so now, hopefully this all should work. I'm gonna go ahead and hide the old sketch so that hopefully it doesn't select it by accident. And now we are going to go to features, swept boss base. Okay. And hopefully after we made that coincident with the 3D sketch, hopefully this will happen rather quickly. Okay, yes, it looks like it is generating, and that looks pretty good. Okay, so now I will go over the motion study. To start a motion study, what we're going to do is we're going to go to new. We're going to create an assembly. You have to do a motion study in an assembly. Okay. So now what I'm going to do is I'm going to put my loop that I just made in, and I'll also put the steel ball in. Okay. Whenever I start an assembly, whenever any of you start an assembly, it would be a good idea to first. What I do is I float the component I first put in. So the first component you put in, it will automatically fix it. I like to float it, and then it'll allow me to mate the origin. So I could click mate. I could click the origin, and I can also click. So yeah, so. Let me just clear selections and show you. So I could click the origin of the part. So you can see from the tree view here, there's the origin of the part. And then, come on, let me select you. There we go. Origin of the part, and then also the origin of the assembly. Okay. And I also make sure I check off align axes. Okay. That looks pretty good. So I'm going to click check mark there. Let's move our steel ball a little closer. Okay. What I had done before was I actually went in and I made my guide curve sketch for the sweep that we made earlier. I made that visible, the 3D sketch, just so that I could use some of these points to mate the ball. Okay, so we need to put the ball at its starting point in order to run the motion study. So we're gonna just briefly mate it. So we're going to take the ball. I clicked the ball first so that it selected it. But we're going to make that ball to the endpoint of that sketch, okay, and make it coincident. So we're going to click check on that. And then we're also going to make the ball to that, the downward slanting surface, and click check on that. Okay, so now the ball is positioned right at the top. And now kind of stupidly, we're going to delete those two mates that we just made. So right click, so shift click them both and then right click and then delete. So really, I just wanted it to be put positioned there. And now what we can do is we can go into our motion study. So down here in the lower left-hand corner, you see the motion study one. Okay. So I'm going to click on that. I'm going to make my screen here. Come on, let me make you a little bit bigger. There we go. Come on. Come on. If I hover over it enough, it lets me do it. It's so fleeting. Why did the designers allow it to be that fleeting? Okay, so first thing we're gonna do, come on, there we go. Okay, so make that bigger. And then we're going to do, instead of animation, I want you to do a motion analysis. If you don't have that, you should be able to go up to sorry, Zoom is in my way, but you should be able to go up to the add-ons up here, from the options, do add-ins, okay? And you should be able to add that motion study to it. Okay, that's the one that'll be like kind of most accurate. So I'm going to go down to motion analysis. Okay, let's expand all that so we can see it a little bit better. So the first thing we want to do when we make our motion analysis is going to be a really simple motion analysis, very basic. But what I'm going to do is I'm going to add a contact mate. Okay, so I'm going to make both the ball, whoops, I'm going to make both the ball and the uh, the loop that we made. Um, we're going to make those both connected. Now, we're going to do this sort of the easy way and select materials. So I can do steel for the ball, which is going to be the first one I selected. That's the first one on the list. And then two will be we'll select nylon. Okay. That's probably going to be the two closest ones to what the print will actually be made out of. Okay. Now, if I wanted to unclick material, I could vary my friction, both my static and dynamic friction. Um, but I'm gonna just keep the materials, and we'll keep with our preset materials, and that way it locks those out for the default values. Okay. So great. We're going to, yep, and we're going to do the solid bodies. So those are contacting. Okay. The next thing we're going to do is we're going to apply gravity. So adds gravity to the thing. Let's also expand this. Made it small for me. We're going to do well. So particular me in particular. I'm going to do it in the Y direction. You can see the Y is kind of what's up in this particular assembly. But yeah. So the Y direction is where we're going to apply our gravity. And yeah, it won't let us change it, but that's 9.8. I'm actually going to change this at this point to meters, kilograms, seconds. Okay, and we could go over here. So there's another tree view for your motion study in the lower left-hand corner. And I could go back into that gravity, right-click it, edit feature, just like I do a lot of other features in SolidWorks. And okay, yeah, 9.81 meters per second. That is definitely accurate. Okay, cool. So now what I'm gonna do, just to modify a couple of things, we have most of it kind of set up. We could start the calculation, but I want to do a couple of things. For one, we don't need this to go for so long. I can make it like 1.5 seconds if I wanted to. That would, shorten the computation, and it's gonna go through the loop and do its thing in like less than a second. So that's all we really need. Now let's make some plots. So what I'm going to do is we are going to plot the ball. Okay, we're going to plot it. Oops, accidentally minimize those. We're going to plot it in terms of displacement, velocity, acceleration. That's going to show us what I want it to show us. I want to do two of them. I'm going to do linear velocity in the Y. Okay, we're going to create a new plot. That's what we have to do for the first one. So we're going to click check on that. Under results, it shows my different plots. And then what I'm going to do is I'm going to go back to results and plots, make another one. Again, focus on the ball. Category will be displacement, velocity, acceleration. Um, and then we're going to do the linear acceleration. And then we're going to do add to existing plot so we can see them right on top of each other. If you forget to click that, it annoyingly kind of doesn't let you put them both on the same plot. If they're on different plots, it's not the end of the world, but it is easier to analyze once they are on the same plot. Select the valid result component. Oh, sorry. Y component again. I forgot to select that. There we go. Okay, cool. So now we're able to calculate the results. That's what it's prompting me to do. It's, probably telling me I've done enough. I could calculate the results. So we could calculate those now. Okay. And we can see the ball has moved. Okay. So we have some fancy plots here. After we ask it to calculate with this guy down here, we could play our thing, okay? And what you might run into is like it might be zoomed in on a weird view like this, and then every time you try and zoom out, it brings you back. There you go. So what we could actually do is go over here to orientation and camera views. Well, got to stop it. Then you could right click, and then I could disable playback of key views. Okay. And then now this will basically play from any location and it'll like still repeat from any location. Okay. And you can see it does our analysis. Or it does the motion. Okay. Now we can take a look at this thing. In fact, we can slow it down and make it go really slow. And if we watch here, okay, a couple of interesting things happen. You can see it doesn't actually go through a smooth path. Okay. But it looks like it wants to stay on the track, which is good. It bounces around a little bit. And what might be interesting to see would be the acceleration and velocity plots now. So let's view those. So I can go ahead, show plot, and show plot. Okay, looks like it didn't put them on the same one as we asked it to. But either way, we could see for acceleration, like when the ball bashes around, so if we look at what is this timestamp, you could see that is around that point there. We could see the ball kind of maybe leaves the track briefly and then has a really high acceleration. Let's see if I could pinpoint the exact acceleration point. So we could even move the timestamp around a little bit. That's too much. So we need something at like 618. Oh yeah, so there we go. Acceleration is peaked there, and acceleration is peaking about there because that's right at the point when it's, after it's left the track, it's smashing into that surface there. So that's the initial contact point. Okay. And what's interesting is right before that, okay, it looks like it is airborne. Okay. So we're going to look at this in the plot. Okay. So if I click this, I can or right click it, I can export CSV. Okay. I'm going to say steel ball video underscore one underscore acceleration underscore two because I already did one for acceleration. Okay. So let's take a look. All right, and we're gonna look at around the half a minute mark. Looking around this sort of area. Okay. So let's open that in Excel. Okay. Okay. Here's the acceleration one. All right. So now we can see if we go to the about the 0.5 second mark. Sorry, I was saying 5 second mark before. Yeah, we look around like the 0.45 second mark around where we have our plot at right now, and we could see acceleration goes to 9.8, which is what gravity is. Okay, which makes sense. Obviously, that's what we told it to do, but it's just kind of interesting to see that when it does get airborne for this brief amount of time, for like less than a second, we are getting the acceleration due to gravity. Yeah, so that's kind of fun. All right. So yeah, that's kind of most of the things that you're able to do with the let's just X out of these. With the motion study, obviously we have our plots here, and we could plot in a lot more dimensions, but what I care about for this assignment are the acceleration and velocity in the X direction. Okay? After doing the analysis, the analysis went pretty well. The ball did stay on the track. Okay, but we learned something from this vertical wall. Although, maybe we thought like the ball should have stayed in contact with this wall a little bit better. Seems like it does actually want to leave it. Okay, at least in the eyes of our simulation. Okay, and as that's something that might actually happen. We'll go ahead and we'll modify it. So. We'll exit out of the motion analysis. We'll go back to the model. Okay. And let's alter it slightly. So we can go here. We could go back into our loop. Okay. We can edit the part. Okay. I'm going to go down to the sweep. We'll go to the 3D sketch. Okay. And we can do a couple things. Well, for one, let's show our other sketch. Okay. And then instead of making it, we could check out our relations. I can make that one. I could delete that. I can delete that. Okay. And we could add some smart dimensions now. And I could dimension this guy to be 1 inch. Okay. That makes sense. I can also dimension this guy to be 2.5. That's good. Okay. And then now what I can do is I could actually change this angle to not be vertical. Okay, wait, hold on. Yeah, that makes sense. I have to delete the vertical relation here. Okay. Yep, that one's along Y, so we're going to delete that one. And we're going to make this one. Let's see if we can change the angle from here to here. Okay, cool. And we could make this, we could probably make it just 80 degrees. Oh, sorry, that's the wrong way. That's the wrong dimension. 100 degrees. Oh, let me change you. 100 degrees. Okay. And critically, we will also make it so that you and you are tangent. Okay, just like that. All right, excellent. And we are fully defined. Let's exit that sketch. Okay. And we'll exit the part. Um, sorry, my Zoom banner is in the way. And let's rebuild everything. Okay. All right. So yeah, so we've modified that part slightly there. In addition to making this comply to its motion study, we also wanted to sort of work in other ways. And from experience, I found that like if you print these things as the track, they normally don't stay balanced very well. So if we go in here and we edit the part, we could probably even take a look at some of the mass properties. So if we go evaluate and we go to mass properties, um, don't want to move that. If we go to, yeah, so we could see that is our center of gravity. And our center of gravity is over that portion there, which means it's going to want to tip and kind of roll over because that portion of the loop is round. Okay. So what we need to do, basically, I showed you the mass properties. You go under when you edit the part in an assembly, you could go under evaluate, or you could find this just like in a part document in SOLIDWORKS. But we could find that little pink thing is past, or in my case, to the left of the center point of this loop, which means it's going to want to tip over like that. So we want that center mass to be like over like the part where it's going to be standing on. Okay, so like if you create a table where the center of mass is not positioned in between the table legs, the table's going to tip over. Okay, so now what we can do to widen our table legs effectively, as we're editing this part, we can go onto the bottom. Nope, don't want to do that. Want to get out of mass properties. Sorry. But what we could do now is we could go onto the bottom surface there. You should have one if you made a horizontal line. So we're going to go onto the bottom surface there. We're going to sketch on it. Okay. And we're going to draw three squares. One square is going to go all the way around the part. Second square is going to go from the corner of the first square to the lower left-hand corner of like whatever's on your part. And you need to be normal to this plane to do it, and it should do that automatically for you. And then we're going to go from the other corner to there. And again, you don't have to do this exactly like this. I'm going to shift click. I'm going to make both of these squares of equal length. Okay, so it's nice and centered. Okay, and I'm going to dimension that to be 0.5 inches. Okay, so that's, nice and symmetrical. I could exit from there. And now I could really, this is just like an example of like a platform you can make. You could do a number of things. You could even probably just have a column coming down from there. But it'll make this whole entire assembly sturdy, especially as you're testing it. So we're going to go over here to features. We're going to extruded boss base, and we're going to select selected contours. I want to select, no, not that yet. I don't want to do thin feature. Sorry. Select just all the geometry. No, I don't want to do thin feature. Can I just do the outer one? Okay. Why won't it let me not do a thin feature? There we go. Okay, so we're just selecting the outer geometry of that and just making a plate. And you know what? I could even flip the direction and make it go into the part a little bit, especially if I make this. Yeah, it's not going to affect the bottom of the track really. And I could even make this just slightly lower, 0.09 inches on that one. Yeah. And that looks pretty good. Okay. And we'll check mark on that. And as you can see, we've made a base that's going to be attached to our thing. And we could go back and check our mass properties. The center mass shouldn't have changed that much, right? So it looks like it didn't. But effectively, we made wider table legs on our table. So we know the part is going to be stationary. Okay, now just for kicks, we're going to recalculate this. So let's recalculate everything. Okay, looks like it did recalculate it. And let's go ahead and play that back. Okay, cool. Looks like it's going to stay well in contact with the track. That should be good. We know it stays in contact with the track. So yep, mission accomplished.